Hi class, welcome to Unit 3, Lesson 9. We will look at electromagnetic induction today. So today's learning goal is students will be able to demonstrate an understanding of law of electromagnetic induction and Lenz's law. I know I've achieved these goals if I can describe in detail the law of electromagnetic induction, factors affecting electromagnetic induction, and Lenz's law. Investigate the Faraday's experiment. Solve problems related to electromagnetic induction, and apply learning and thinking to daily life problems. So we've seen this far, we've talked about current going through conductors and objects, and it obviously produces a magnetic field. But can the other order happen? Can a magnetic field produce an electric current in a conductor? Well, the definition of electromagnetic induction is the production of electric current in a conductor moving through a magnetic field. Faraday discovered that in order to produce an electric current, the magnetic field needs to be continuously changing. So Faraday's experiment had a very clever setup. So Faraday investigated electromagnetic induction using a device he built himself. He used a solenoid around a wooden core connected in series with a switch and a powerful battery to form a primary circuit and a secondary circuit, consisting of a second solenoid around the same wooden core. So we have the primary and secondary. Primary, secondary. And it was around the same wooden core wired in series with a galvanometer configured as an ammeter or current measuring meter. Closing the switch in the primary circuit produces a constant electric current in the conducting wire. This constant electric current produces a magnetic field in the primary coil. And this change of the magnetic field induces a voltage and an electric current in the secondary circuit. And so the key piece we're looking at is electric current in the secondary circuit because of the change of magnetic field. So the key piece is the change in magnetic field. And so once the magnetic field is stable and no longer changing, the electric current in the secondary circuit no longer exists. So it's imperative that we have this change in magnetic field. To improve his results, Faraday built a new device, now called Faraday's ring, which utilized an iron ring to increase the magnetic field inside the solenoids. So in Faraday's iron ring, even though the magnetic fields are stronger than in Faraday's first apparatus, an induced current is produced in the secondary circuit only when the primary circuit is turned on or off, changing the magnetic field. So even though he tried to see if the material would help, it did make the magnetic field stronger. The effect was still evident that you needed this changing magnetic field in the first one to produce the current in the second solenoid. So his experiment leads to the law of electromagnetic induction, which says his finding: an electric current is induced in a conductor whenever the magnetic field in the region of the conductor changes with time. So that's exactly what he found to be, and that's our law. Induction means that one action causes another action to happen, often without direct contact. Faraday brought a permanent magnet near a conductor, but not in direct contact with it, and induced a current in the conductor. The electric current was produced only while the magnet was moving in the vicinity of the conductor. So true induction we have. So we could see proof of this again, not only in his experiment, but testing the law of electromagnetic induction. Faraday's law of electromagnetic induction can be seen when we plunge a bar magnet into a solenoid connected to a galvanometer or ammeter, or configured as an ammeter, a current reading meter. So we have in the first in A here, we have when the south pole is pushed into a coil, a current registered indirectly by a potential difference across the terminals is produced in the coil. So as this is being pushed in at V speed, but as soon as that V turns to 0 and we stop pushing it, that's when this current drops to 0. Because the magnetic field in the area is not changing when it's not moving. And so when we again move into the opposite direction, we have a current in the opposite direction. So when we pull it this way, notice our current of same magnitude, but in the other negative direction here. And then with the same V, but as soon as that V goes to 0 again, bam, we get 0 current once again. So the conclusion here, what Faraday found, is the current is produced by a changing magnetic field. And the greater the change, the larger the induced current. And that's exactly what Faraday found. So some factors in this type of induction. For coil conductors, they have more induced electric current in it than a straight conductor does. 2, the number of loops in the coil. The greater the number of loops in a coil, the more electric current can be induced for a given change in the magnetic field. And lastly, number 3, the rate of change of the magnetic field. So we said that the current comes from changing of the magnetic field, and intuitively it makes sense that the more you change this, the more current you're going to get. And so the more quickly you move the magnet into or out of the coils, as we saw, the greater the rate of change of the magnetic field is happening. And because of this, a higher rate of change, this higher rate of change causes a larger induced electric current in the conductor. So intuitively, it makes sense. Our intuition matches what happens. So that brings us to Lenz's law, which says when a current is induced in a coil by a changing magnetic field, the electric current is in such a direction that its own magnetic field opposes the change that produced it. So this one is obeying the conservation of energy and is the valid one, and is Lenz's law. And this one is violating, so it's not this. But why is it this right one? These are the two scenarios it can be. And why is it this right one? Well, Lenz reasoned that when the field from a moving bar magnet induces a current in a solenoid, the current gives rise to another magnetic field. And so this can be in either one of these directions, but which one is valid? So let's assume that the current spirals toward the magnet when a north pole is pushed into the coil, as in this section, so figure A, this one. The right-hand rule for coils then tells us that the right end of the coil becomes the south pole, attracting the magnet. Lenz figured that this situation is not possible because the attractive force will speed up the magnet, increasing its kinetic energy, inducing a larger current, more energy, and increasing the induced magnetic field with the magnet speed up still further, making its kinetic energy even higher. So this attraction is going to more and more quickly, more accelerating more kinetic energy and more quickly. But we can't really have this, since the total energy of the system can't increase like this without it being transferred from somewhere else. And so this assumption has to be false, and the current in the solenoid has to spiral away from the incoming north pole, as in B, because of this key piece here. total energy of the system cannot increase. So you can't be gaining all this kinetic energy for no reason, and just more and more because it's just attracting more faster, and it's making, or we're already moving into the magnet, and so it's the attraction forces add on to that, and so that can't be. And so therefore the near end of the coil has to be a north pole. So this has to be a north pole. So we don't have that attraction, this added kinetic energy. And so the moving bar magnet induces a current in the coil, which produces a magnetic field in opposition to the inward motion of the bar magnet. So now that there's no attraction, now there's actual repulsion, some work has to be done to push past this force now pushing this way. We have repulsion pushing the magnet that way. So that means now that some work has to be done in pushing the magnet into the coil against this opposing inducing field. And this work is now transformed into electrical energy in the coil. And so we have proper maintaining of total energy of the system, versus before if we had this free attraction and then negative work, essentially it doesn't work like that. That's invalid. So the idea for any Lenz's law problems, if you're asked to find the current's direction, it's in a way that the magnetic field of the coil opposes the motion of the magnet. So we've established that we have repulsion. It has to be north-north, can't be north-south, and so you're always given the direction of the magnet, so it's going to be traveling into this direction. So to oppose that, that means our magnetic, for the coil, that means the magnetic field has to be going like this through the coil, right? Strictly for the coil. Ignore these blue lines, these are just for the bar magnet, but for the coil itself, our B would have to be like this to the right. So that's our thumb for coils, remember our right hand rule, and that means if that's the case, then our fingers curl in the direction of this diagram. And so that's what it's meant, that the electric current is in such a direction that it's the coil's own magnetic field opposes the change that's producing it. What's producing it is this direction of the magnet. So likewise, if the magnet is being pulled this way, to oppose that change, we need to now have a B direction like this. So that's our thumb, and so if we do a B direction of that, we notice our fingers curl the other way, the arrows would be flipped, and in fact we would have this diagram, except we would have it going this way. That's the only thing that changes. So to make this valid, we only need to change the direction of this magnet going this way, and we're all good. But that's what it means by it's opposing. So the coil's own magnetic field, its own B's, oppose whatever way the bar magnet is moving. So we have either direction to oppose which way it is. So if it's coming toward, then it's going to oppose it, and if it's going away, it's going to go it's going to try to attract it back this way for the coil. And so that will always tell you your thumb direction, because we're working with coils, right? That's the direction of the magnetic field B, and so our fingers curl in the direction of the current. So the idea is for these questions, oppose the direction of what the magnet is. So if it's coming in, it's this way. If it's going here, different color. Here's what the bar magnet would be doing. And here's what the coil does. And so if the bar magnet is coming to the left, the coil is going to oppose it and go to the right. And likewise, if it's going away to the right, the coil is going to go to the left. So that will give us our B. And once we know our B, we put our thumb there, and we can tell easily which way our fingers curl, and that will be your answer, which you usually ask for, which direction you put the arrows. So hopefully that clears this a little bit up. So that's Lenz's law. So his law has some fantastic applications in the real world. One of them is the drop tower rides that you see in amusement parks. So the way it works is each cart on the ride has permanent magnets under the seats. After 45 meters of free fall, an electromagnetic braking system kicks in. Along the bottom third of the tower are copper strips mounted vertically on the tower, and when the cart falls and the permanent magnets move past the copper conductor, an electric current is induced in the copper. The induced current then produces a magnetic field. Applying Lenz's law, the induced magnetic field must oppose the field that created it. The opposing repulsion force acts to create a reliable no-friction braking system. And there, oh. So that's the key. And because of that, this electromagnetic braking system is able to work automatically, and it doesn't wear out. Magnets just, they don't wear out, whereas like some sort of mega brake pads or something, you'd have to replace them, you'd have to monitor them. But the way these magnets work is they work naturally and there's no wear and tear on them, which was really amazing. Some other applications of electromagnetic induction are induction cooking. Cooking uses an induction cooker that involves a rapidly changing magnetic field. Always have changing magnetic fields in induction in the stove element, which induces an electric current in the pot. The electric current heats the pot because of the electrical resistance of the pot. And metal detectors in airports. Metal detectors use a coil that generates a rapidly changing magnetic field. This magnetic field induces a current in any metal near it that it finds. The induced electric current in the detected metal also produces an induced magnetic field of its own. And so the readers pick up on these and is able to detect metal. And famously, our northern lights are produced as a result of Earth's magnetic field interacting with the charged particles from the sun in our atmosphere. And so they're reacting with charged ionized particles. And so that's going to be everything for today.